Hello everyone and welcome to lecture. In this lecture we'll be talking about how to correctly define the inverse trigonometric functions and how to use them to do various things and simplify various trigonometric equations. So recall that to define an inverse function, if you have a function on some domain, we define the inverse in the following way. Say if f is, say, some increasing function on a domain, we can define the inverse function of f by looking at the reflection of this function about the line y equals x. So specifically for this function that I've drawn here, it's going to look like a reflection of this function. I'll actually do it in green about the y equals x axis. That's going to this reflection is going to look like this exactly. We're reflecting over the line y equals x. This is geometrically how you can define the inverse of any function that's an increasing function on some interval. So the idea here is that we want to do this for all of the trig functions, and we can do this for all of the trig functions. We have to be careful in order to ask ourselves exactly what the correct new domain of that function is going to be, but you see that it's clearly possible to do this for any sort of relationship that you have where a function is increasing on some domain. So the interesting thing here to think about is what this is going to look like for the trig functions, the specific trig functions. So if we open up a plotting window, I like to use what's called the Desmos graphing calculator. Make this a little bit smaller. So the first function we want to visualize is the function. We'll start with the sine function and see what the inverse of the sine function is. And so this is a plot of the sine function right here. We'll zoom in a little bit. Plot the line y equals x. And then in terms of notation, we call the inverse of the sine function what's sometimes known as the arcsine function. And you can see that clearly that green curve right there is the reflection of the sine function over the domain from -1 to 1. And this is where it's important to note that the sine function is only increasing when x goes from -pi/2 right here to pi/2. And so the sine function is increasing on this interval from -pi/2 to pi/2, which means that when we define the inverse sine function, we have to restrict ourselves. The domain of the inverse sine function is actually only from -1 to 1 because of the fact that the sine function is increasing, right, from -pi/2 pi over 2 to positive pi over 2 right here, or as sine goes from negative 1 to 1. So you see that the arc sine function has a restriction on its domain from negative 1 to 1. But this is exactly what the arc sine function looks like, and is the correct way of defining this function, this inverse trig function. So geometrically speaking, this makes a lot of sense. Now it's important to stress that this this function, right, has a restricted domain. That's the first thing that's very important to stress. And the second thing that I want to point out that you should take caution is that some books for the inverse trig functions use a notation of sine to the power negative 1. That's perfectly fine, but we're going to try and stick to using the notation arc sine, or arc, before any of the inverse trig functions that we're calculating. So arc sine of x, or sine to the negative 1 of x, are the inverse. It stands for inverse sine. This is not the same thing as 1 over sine of x. We've already seen that this actually has a different name. This is called the cosecant function of x. Right, so these two things are not the same, and this is one of the reasons why I don't like using this to the power negative 1 notation. I think it's a better notation to use the arc notation, because this clearly is indicating that this is a new function and a different function. It's not the same thing as 1 over sine of x. But even if you see this notation in any math book that you might read, 1 over sine of x is not the same thing as sine negative 1 of x. This does not mean raised to the negative 1 power. So we've already seen, though, we've seen that the graph of arc sine of x, what it looks like, and we have that for any x between pi over 2 and negative pi over 2, we've seen that we can define the arc sine function by saying that, well, if y is equal to sine of x, for x in this interval from negative pi over 2 to pi over 2, then that means that x has to be equal to arc sine of y, and vice versa. So specifically, we've seen that as well as the domain of this arc sine function is the interval from negative 1 to 1, because these are all the possible values of y that we can plug into the arc sine and get an x value in the interval from negative pi over 2 to pi over 2, as well that the range of the arc sine function is the interval from negative pi over 2 to pi over 2. So let's see an example of how to use this. For example, let's try and calculate arc sine of sine of the angle 3 pi over 4. And you might just jump right in and try to calculate and say that this is in fact equal to 3 pi over 4, but we have to be a little bit careful here, so we don't want to jump in and do that. And the reason being that 3 pi over 4 lies outside of the range of arc sine, which we've already established is the interval from negative pi over 4 to pi over 4. So in order to get around that, we have to be a little bit more careful. We can still look at sine of 3 pi over 4. right, and use the fact that sine of 3 pi over 4 is in fact equal to 1 over the square root of 2. If you don't remember that, you can go ahead and draw out the unit circle from a previous lecture. Where you'll see that this is exactly the case. Remember that 3 pi over 4 corresponds to an angle of 3 times the angle 45 degrees. Pi over 4 is, or pi over 4 radians is equivalent to 45 degrees. So it's 1, 2, 3. It's right here in the second quadrant. So this angle right here is 3 pi over 4. Right, and then that means that, remember, this is the unit circle, so on the unit circle, x equals cosine of theta, and y equals sine of theta. So sine of the angle 3 pi over 4 is the y coordinate of this triangle. It's like cosine of 3 pi over 4 is the x coordinate of this triangle. And this triangle is 45 degrees, 45 degrees, 90 degrees triangle, which means that the x coordinate here is going to be negative 1 over the square root of 2, and the y coordinate at that point is going to be positive 1 over the square root of 2 in order to make this the unit circle. So sine of 3 pi over 4 is 1 over the square root of 2, and then we have to, when we're taking the arc sine of this, so arc sine of 1 over the square root of 2, we can only look in the interval. Oh, I have a little bit of a typo here, sorry about that. It should be negative pi over 2 to positive pi over 2. So we can only look in this interval right here, because this is the range of arc sine. So sure enough, inside this range from negative pi over 2 to pi over 2, the arc sine of this angle, the arc sine of 1/2, is going to be exactly just equal to pi over 4. Because this is the only angle inside this interval that gives us this. So it turns out that the arc sine of 3 pi over 4 is exactly this angle pi over 4 right here. Right, so this is it. This is the way that we kind of go through and use the inverse trig functions in general to help us figure out relationships between angles. And we'll see as we kind of move along that there are a lot of different identities that are help us relate the trig functions to the inverse trig functions and help us simplify certain trigonometric expressions. So we'll do one more inverse function. This is going to be the inverse of the tangent function, or arctangent. This is the function that satisfies the following. It's if y is equal to tangent of x, where remember tangent of x is the function with a domain, a strict domain from negative pi over 2 to pi over 2, and a range of negative infinity to infinity. So that means that the arctangent function, or the function that gives us x in terms of y when y is equal to when y is equal to tangent of x is going to be a function that has a domain of negative infinity to infinity and a range of negative pi over 2 to pi over 2. And we'll take a look at the plot of this and directly verify this in our plot window. So here we have the tangent function, y equals tangent of x. We can plot out the line y equals x here. And then lastly, we will plot out y equals arctangent of x. You see very clearly that what we kind of calculated before is exactly correct. The tangent function is in red here. It has a natural domain from negative pi over 2 to pi over 2. And it has a range from negative infinity to infinity. Take the line y equals x in green here, and we reflect the tangent function over the line y equals x. And sure enough, the inverse tangent function, arctangent, has a domain from negative infinity to positive infinity, and a range from negative pi over 2 to pi over 2. So this function is also very, very useful. And the third inverse function, inverse trig function that's very useful to us in calculations is arc cosine, the arc cosine function. So I'm not going to go through the graph of this, but I recommend you go through and do the graph of this. I also recommend that you go through and do the inverse cosecant, secant, and cotangent function. That'd be a very good idea to go through and just kind of verify to yourself that you can go through and calculate the domain and range of those inverse functions as well, because all of them show up in various aspects of applications, and definitely if you move on to, say, a calculus course, these are functions that are going to be very, very, very important. So we'll go through and look at our cosine of x, which is the function that satisfies, well, if y equals cosine of x, then arc cosine of x has to satisfy, arc cosine of y has to satisfy that x is equal to arc cosine of y. And maybe I will open up the plot in a second just to show you that this is definitely doable. You can do it for a good exercise would be to do it for the inverse cosecant, secant, and cotangent functions at home. By the way, the graphing calculator that I'm using is a free online tool. It's called Desmos. Right, so you can just Google Desmos and go to the Desmos website to get these nice plots that you're seeing kind of done out. It's a very, very useful tool for visualizing functions and kind of helping you argue and really, see geometrically what you're doing when you're talking about various functions. So we know that the cosine function is going to be monotonic or decreasing from 0 to pi. And from 0 to pi, this is the interval that we have to take for the domain of the cosine function, or the natural domain of the cosine function. And from 0 to pi, the range of the cosine function is the interval from negative 1 to 1. So this is going to be the correct range and domain of the arc cosine function. So the arc cosine function is defined from, or has a domain of the interval from negative 1 to 1. And a range of the interval from 0 to pi. And I'll open up the Desmos window again so we can see this done out in what it looks like using our standard method of going through and arguing for the inverse function based on the graph. So we plot out cosine of x here, plot out the line y equals x, and then plot out the function arc cosine of x, and you see very clearly exactly what we were talking about. The cosine function is decreasing from 0 to pi right here, and when we reflect this along the line y equals x, we get that the inverse function is the function with the domain from -1 to 1 and going from 0 up to pi right here. So I encourage you to do this for the cosecant, so arc cosecant, arc secant, and arctangent as well, just so you can kind of get a feel for what these inverse functions look like, and how to actually graphically get what the function is and what it's saying about the relationship between the original function and the inverse function. But we can look at an example of how to kind of combine these, and using a combination of these trig functions and the inverse trig functions, you can get very, very powerful relationships. So let's say, for instance, you want to express the following. Say you want to find the sine of arc cosine of 2x for x in the interval from 1/2 to -1/2. This is something that would commonly come up in a calculus course, specifically in like a calculus 2 course or an integral calculus course, where you're doing sorts of what are called trigonometric substitutions to evaluate integrals. So the idea is to be able to re-express all of this as just a function of x. If we can do that, is there a way of doing that? And sure enough, there definitely is a way of doing that. If you, again, consider the unit circle, where this is the x-axis, the y-axis, and we'll make our unit circle. You remember that arc cosine of 2x here, you can just call it theta, say. It's an angle inside the range of arc cosine of x. So it's an angle that has it's between 0 and pi. It's going to give us a triangle. It's a right triangle. With a radius of 1, because it's on the unit circle, and an x distance of 2 times x right here. This is the x-axis right here, and this distance is 2 times x. And we know that on this unit circle, the y-coordinate on the unit circle is equal to sine of any angle theta. So sine of this theta, whatever it is going to be the y-coordinate on this unit circle. We know that, say, on the unit circle we have that this distance squared plus whatever y squared is equal to 1. And we're on the top of the circle, so I might even just kind of erase the bottom part of the circle, because we're only interested in theta from 0 to pi, because this is the correct range for the arc cosine function. So let's do that. We'll erase. So if we solve this equation right here for y, we get that y is equal to the square root of 1 minus 4x squared. So this expression algebraically is the same thing as the square root of 1 minus 4x squared. So this is a very, very powerful tool, these inverse trig functions, because they can all be related to one another and they can all be used to simplify things algebraically. But that will conclude this lecture, and thank you very much for tuning in. I hope you learned something.